Let's now consider the graph of the logarithmic function. But first, let's consider the graph of the square root function. So I've graphed the square root function here. We have y is equal to the square root of x. And as before, we took the square root of 4. And so that means whenever x is equal to 4, we come up to the graph, and then y is equal to 2, right? So the square root of x is equal to y, right? Square root of 4 is equal to 2. Okay, so this is just a graphical analog that we're going to consider. Okay, so here is the graph of the log of x, right? So let's consider a couple of points on the graph. So first of all, we see how that the log of x is sort of square rootish, right? It comes up and over, and it starts off steep, and then it starts to flatten out, right? Okay, so let's consider a couple of points on this graph. Let's first consider the point 1. The log of 1 is equal to 0, right? The log of 1 is equal to 0, and we can see that in the following way, right? Let's do an example. If we take the log of 1, log base 10 of 1, what this is the procedure that this is inferring is what? This is 10 raised to the y power. 10 raised to the y power is equal to 1, right? So what value of y will satisfy this equality? The only value of y that will satisfy this equality is y equals 0, because 10 to the 0 power is equal to 1. So y is equal to 0, right? And we see that that's true here, right? We see that at x equals 1, y is equal to 0. It's not positive, it's not negative, y is equal to 0, right? Okay, one other point on this graph to consider is at the point x equals 10. And at x equals 10, the log of 10 is equal to 1, right? So we're considering base 10, right? We're going to consider other bases in the next tutorial. But if we have the log of 10, like so, and this is log base 10, right? Remember, the procedure that we're being asked to consider is 10 raised to the what power is equal to 10, right? Well, 10, if we write 10 like this, it's understood to have a 1 power, right? So we see that y must be equal to 1, because 10 to the 1 is the only thing that equals 10, right? So then y is equal to 1. And so on the graph out here at x equals 10, we take the log of 10, and that gives us a y value of 1, right? Okay, so the reason that the logarithmic function is useful, now incidentally, the log of 0 is undefined because the graph is asymptotic at the y-axis, and the log of 0 is undefined. Because think about what you're asking. You're saying 10 raised to the what power is equal to 0, right? Well, there's no value of y that will satisfy this equality. And because there's no value of y that will satisfy this equality, it's undefined. The function is undefined at that value, right? And so the function shoots down, and it shoots down to y equals negative infinity, but it gets ever so close, y equals negative infinity, and it gets ever so close to the y-axis without ever actually touching the y-axis. So it's asymptotic to the y-axis. And that only occurs between 0 and x equals 1 is whenever the values of y are equal to negative. So the log of 0.5 will be a negative number, right? And so on for any number in between 0.2, 0.3, 0.4. The log of any fraction of 1 is going to be equal to a negative number. And then we see that it tapers off very quickly, right? And the reason the logarithmic function is so useful is consider the log base 10 of a million, which is 10 to the 6, right? So what this is inferring is 10 to the y, 10 to what power is equal to 10 to the 6, right? So y is equal to 6, right? So the reason it's useful is because you can set up a logarithmic scale, and huge numbers, when you take the log of very big numbers, such as 1,000,000, they give you, very small values, right? And so if you're plotting very large values, rather than having a piece of paper that's, 50 feet long, you can use a log scale and you can plot it in a manageable space, right, on a piece of paper. And so that's why the logarithmic scale is so useful. Okay, I'm going to step out to the side and give you a clear screenshot. We're going to consider some other bases that show up, especially in the natural logarithmic number. So I'm going to step to the side.